This video series will be about the complex exponential function and all of its friends, the trig functions and the logarithmic functions. We're going to define the complex exponential function via power series as this power series, the sum from n equals 0 to infinity of z to the n over n factorial, and we either write it with exp of z or e to the z. There's no difference between these. We may write exp when we have a lot of stuff to plug in and it becomes awkward to put everything as a superscript. Note, we already calculated the radius of convergence for this power series earlier and it was infinity, so this series converges absolutely for all z. Okay, so one of the main properties of this function is that its derivative is itself and it turns addition into multiplication. So exp of z times exp of w is exp of z plus w for all z and w in the complex plane. So let's prove this theorem. Well, the part with the derivative just comes from doing a term-by-term differentiation of the power series. So if you take the derivative of this, an n would come down to cancel the n and the n factorial. So you'd get z to the n minus 1 over n minus 1 factorial. This series goes from 1 to infinity, and then if you shift your indices, you get back to where you started. So this shows that the derivative of the exponential function is itself. Then you can use this property to show that the exponential of a sum is the product of the exponentials. So to do that, we look at the complex derivative of e to the z plus w times e to the negative z. Obviously, if we already knew the property we wanted, this would be e to the w, and we can just show that directly. So you take the derivative and use the product rule and the chain rule with the z plus w. You get the derivative of the first is just e to the z plus w times the second, plus the first times the derivative of e to the minus z. We'll bring a minus in front and leave e to the minus z here. So we get 0. And since the complex derivative of this is identically 0, you get that this function has to be constant. And if it's constant, you can plug in the value at 0 to get its value everywhere. So you plug in 0 and you get e to the w, and e to the 0, we know e to the 0 is 1 just from the power series. So you get that this is equal to e to the w. That still doesn't quite prove what we need because I still have e to the minus z, but I can put in w equals 0 and get e to the z times e to the minus z is 1, so that gives you that e to the minus z is 1 over e to the z, which is the property you'd expect, given what we know about exponentials for real numbers. And using this, you can multiply both sides by e to the z to get e to the z plus w is e to the z times e to the w. Now let's look at a bunch of other important facts related to the exponential function. Here are a bunch of straightforward facts that come from the power series definition and the additive property of the exponential that we just proved. So the first thing is that the conjugate of the exponential of z is the exponential of the conjugate. You can view this just straight from the power series. Now, we'll see that when you plug in real x into the exponential, it gives you the exponential function you're used to from calculus. For instance, exp of z is positive for x being real. Well, why is that? Well, it's clear. that x of z is positive when x is positive by looking at the power series, but we know that x of minus x is the reciprocal of e to the x. So it has to be positive for every real number. And also you can see from the power series that x of x is bigger than 1 when x is positive, because the power series starts out with a 1, and then positive stuff when x is positive. And by the reciprocal property, you get that x is less than 1 when x is less than 0. Also, you can just stare at the power series and see that it's bigger than x, so x of x has to go to infinity as x goes to infinity. You can also see that the power series is increasing, either by the fact that the derivative is itself and that's positive, or by inspection. Also using the reciprocal property, we get that x of x goes to 0 as x goes to minus infinity. So all the properties that you already should know follow easily from using power series. The next fact is that the modulus of exponential of z is the exponential of the real part of z, and you can get this by taking exp of z modulus squared equals exp of z times its conjugate, but by the first fact you can take exp of the conjugate, and by the theorem we can turn this multiplication into addition, and you get 2 real part of z. And now you can take square roots of both sides, and we know that square roots within positive real numbers are unique, so this positive real number's square root will be equal to this positive real number, which has the property that when you square it, gives you the right thing. Okay, from this property you can deduce that if you get exponential of z having modulus 1, you have to have z being purely imaginary. That's just by the property shown above, that the modulus of exponential of z is exp of x, and we know it's by these properties here that the only way to get the exponential equal to 1 is if x is 0, meaning the real part 0, meaning z is purely imaginary. Okay, more facts. Well, if you take the usual derivative of exp of x with respect to x, you're going to get the exponential back, and using this you can prove using differential equations that this is the standard exponential function from calculus. On the other hand, if I take the derivative of x of iy, the I comes out and I get x of iy. And now we can use this to actually define the trig functions, or if you don't want to go into the details of sort of building the trig functions from scratch, you could use this to understand them more efficiently. We're going to actually do a bunch of stuff from scratch, so you can use all of these power series techniques to define the trig functions and show that they have all of the properties that you're used to. And it's really much more efficient than you might see in a calculus course. So you can define cosine of y to be the real part of exp of iy. So remember, this will be a complex number of modulus 1, and so its real part will be between -1 and 1. And the same goes for sine y, which we define as the imaginary part of exp of iy. So we're building this, the trig functions, so that by definition, exp of iy is cosine plus I sine y. So cosine and sine in this perspective are just pieces of the exponential. And by the derivative property right here, you get that the derivative of cosine, well, you calculate it by taking I x I y, which gives me minus sine, and then likewise the derivative of sine will come out to be the imaginary part of I x I y, which is cosine. So these are the usual properties. And again, x I y is on the unit circle, so cosine squared plus sine squared is 1. On the next slides, we're going to go through in detail how to build all of the properties of trig functions that you're used to. And so you can think of this as reinventing the circle. You might wonder why we'd bother through this. This is a good model for other techniques that might come up where you have a function defined by a power series and you want to prove all kinds of qualitative properties about it, but you don't recognize it as a familiar function. So this can model that process on a function that you may be familiar with.